Vanya.
Hello, 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 I'm here.
Right, can you hear me? Can you see me? You can hear me but
I
not see me,
cannot
I
see
think.
you, but I can hear you well. Yeah,
That's
now I
better.
can see you. Yeah, perfect.
Okay. What I want to try to do is, but before we get started, I want to see if I can work out how to share my screen because I've got slides.
You have to click, I think it's already time. Yeah, it's time. Okay, it's my big pleasure to introduce Gregory Sankaran from Bath, and Gregory will speak about blowups with canonical singularities, and will answer a question posed by Kosher Birka some time ago. Yeah, thank you, Gregory. Yeah.
Thank you. Yes, I was actually supposed to be giving this talk in real Edinburgh, but that's obviously not happening. So I haven't tried this before, and I don't know how well it will work. You can see me, I think, but I can't see you. All I can see is the slide that I hope you are looking at. I can't see anything else, so everything else has to go through Vanya. Okay, so I mean, the story starts with you know, you used to be able to go to the pub after seminars. Obviously, we can't do that at the moment. A couple of years ago, there was a meeting of the Cow in London, and some of us went to the pub. And one of the people who went to the pub was Kosher Birkar, and in the pub, he asked a question. So here's the question he asked. You pick some weights, 4 weights, N1, N2, N3, N4, co-prime, by which I mean only that boldface N is a primitive integer vector, so there's no number bigger than 1 that divides all of the N's. And you take the associated weighted blowup of A4 at the origin. And you look at it and you discover that it has terminal singularities. And his question was, does that mean that there is a bound on the smallest of these weights? So it's not immediately obvious why that's the right question to ask. In fact, I'm not entirely sure that I know even now why it's the right question to ask. And to some extent, I'm taking it for granted that it is because of who asked the question. But there's some sort of immediate evidence for this, as we'll see. But that's the first question that he asked. You know, this looked to me, and you'll see why as I go along, it looked to me as if this might not be so hard. So I actually started thinking about it. It turned out, I did think about it. I wrote to him and I said, well, you know, I think one should be able to do this, and here's how. And he said, okay, very nice. But here's what I really meant. He had a rather more serious conjecture in mind. So he takes, first of all, he drops the requirement that the dimension should be 4. It's now allowed to be whatever you want it to be. And he replaces terminal with epsilon log canonical for some arbitrary epsilon. So you make a weighted blowup of affine space, and just blow up something at a smooth point, weighted blowup. You look at the resulting space, you find that it has epsilon log canonical singularities, and in that case his conjecture was that the smallest of the weights should be bounded by some constant, depending only on the dimension and of course on epsilon. Okay. So let me tell you what we can do. So we means me and Paco Santos in Santander, and we actually show that we show everything. We show that the conjecture is true. So here's the main theorem. This is just a rephrasing of the conjecture. So in any fixed dimension and any epsilon between 0 and 1, there's an integer LED such that if you take a weighted blowup and you have epsilon log canonical singularities, and the thing we call n min, the smallest of the weights, that should be less than this number L. We do a bit more than that. We actually give a precise answer to the question that Kosher asked at the cow. So that's A4 and terminal. And in that case, we know that Theorem 1 tells us that there is a bound, but in this case, we can actually tell you what it is, and it's 32. But there are only finitely many of the n's which give terminal singularities, but all the n's are bigger than 6. So I'll say this more precisely later on, but with finitely many exceptions, the bound is 6, and overall it's 32, and it really is, the bounds are sharp. So you'll see why we're able to give a precise answers in this terminal fourfold case, and not really for any of the others. Okay, so I mean, I should give some sort of motivation for this. Obviously, this being Kosher-Birkar, the birational geometry is the motivation. So I don't know whom I'm talking to. I don't know who I'm talking to exactly, because I can't see the list of participants, but I'm absolutely certain, because Vanya is such a person, that there are people listening to me who know considerably more about birational geometry than I do. Nevertheless, I think I should try and give some sort of explanation of where all this comes from. So if you look at so start by thinking about dimension 3. If you look at the Sarkisov program for threefold, so I suppose you're trying to understand, in some sense you're trying to understand decomposition of birational maps into Sarkisov links. And one of the things you need to understand are divisorial contractions, with where the target is a Fano threefold. Now, it seems that in general, understanding divisorial contractions from a given X, so where you know where you're starting from, that's maybe kind of okay. But if what you know is where you end up, that seems to be more difficult, or at least less studied. And the result that everybody quotes about this, so perhaps it's really the only one, is the result of Kawakita from 2001. So he shows that a divisorial Mori contraction, so I mean Q factorial terminal singularities, with center a smooth point. So you do a Mori contraction and then you find you've got a smooth threefold point. That's actually a weighted blow up. And the weights are 1AB. So the part of this that is the analog of the conjecture of Birkar is that 1. The weights are 1AB rather than something bigger. So in that case, the bound is 1. So that second part is the answer to the question that Kosher asked after the cow, but in dimension 3. And what we're trying to do is to generalize that to arbitrary dimension, and we're also trying to generalize it from terminal singularities, which is implicit in the term Mori contraction, to epsilon log canonical singularities. So a couple of things to say. What I've just told you was told to me by Anne-Sophie, but it's this is, I'm telling you what I think she told me. So if it doesn't make sense, or if it's flat out wrong, that's almost certainly my fault, not hers. But if it's right and it makes sense, that's because she told me. And the other thing, so I managed to give this talk, or talk like this one, a couple of times before everything shut down. One of them, Tom Ducker, pointed out to me that there are Mori contractions, I mean, maybe in a higher dimension, where the center is of positive dimension, not just a point, and which do not have to be weighted blowups. You see, the Kawakita proves that the Mori contraction is a weighted blow up and then tells you what the weights are. And I'm only interested in the second of these clauses, the first part that says it's always a weighted blow up. That's an interesting fact, but it's true for threefolds. I don't know whether it's true for maybe some slightly higher dimensions, but you do need to have the center of the contraction being a smooth point. Otherwise, more complicated things can happen. Okay, right. So I'm now going to change direction completely and start talking about polytopes in d-dimensional real space. And the reason I'm going to do that is we're going to do toric geometry. And so I need a bit of terminology. So I'm going to fix an additive subgroup of RD. Now, usually you will think that this is a lattice, but I don't specify that at the moment. It's just an additive subgroup of RD. And I'll fix a polytope pi, and I'll say that it's hollow with respect to pi if pi intersect gamma is contained in the boundary of pi. So it's got some lattice points, but they're on the faces of pi, and it's empty if all the lattice points in pi, so I'm thinking of pi as a closed polytope here, I didn't say that. So empty means that the only lattice points, the only integer points, if you want to think of it that way, are vertices of pi. So hollow things are allowed to have lattice points somewhere in the middle of a side, empty ones only at the corners. Okay, so usually the position is that gamma is a lattice and pi is a lattice polytope, but that's not necessary, and we will use this terminology in places where neither of those things is actually the case. Okay, so what I want to do is, well, first of all, this is just setting up some toric background. So I'll fix a lattice in RD, and I'm free to change my coordinates, so it might as well be Z to the D. And I'll take a closed rational polyhedral cone, sigma in RD, that's centered at the origin, of a vertex at the origin, and it's generated by some generators Wi, which are primitive integral rays and integral points. And this determines an affine toric variety, which I'll call X sigma. And it also determines a polytope, which is the polytope spanned by the origin and those generators of the rays. So we'll know that X is Q Gorenstein if and only if all the Wi lie in an affine hyperplane, and it's Q factorial if and only if the polytope delta sigma is a simplex. In other words, if there are exactly D of the Wi's. So I think I'm probably thinking of this as not lying in a hyperplane. No, that's just okay. So I want to, that's just some background, and then the basic fact that is going to let us translate all this into toric terms is the following. So let's pick an epsilon, and then X sigma is epsilon log terminal if epsilon times delta sigma, so that's delta sigma, which is the simplex or whatever generated by the generators of the rays and the origin, multiplied, shrunk by a factor of epsilon. If that's empty, then X sigma is epsilon log terminal, and it's epsilon log canonical if the same thing is, well, it's hollow, so it's now allowed to have some lattice points on some faces, but actually it's only allowed to have it on what you think of as the top face, the face not containing the origin. So one log canonical is canonical, and 0 log canonical is what's sometimes just called log canonical. So there's this well-known fact that quotient singularities are log terminal, and that really comes down to the statement that the trivial polytope 0 is empty because everything's a facet. So I've got a picture here. You're to think of the I've called those E1 and E2. I shouldn't really have done that. I've got a cone, and I've got okay. So in this picture, what I've done is I've drawn a dotted line at height epsilon. So the things underneath the dotted line, the lower of the two blue diagonal lines, anything below that is a place which, when I use it, when I pull out that divisor, I'm going to get a discrepancy which is too big, and so it violates epsilon log canonical. So W1, so these are some lattice points, W1, W2, and E1 and E2, and I have to make a toric resolution, so I introduce new rays, the green ones, and they correspond to divisors, and corresponding to those divisors there's a discrepancy, and epsilon log canonical tells me that those discrepancies should be not too big, and the one for W1 isn't, it's above the epsilon line, but the one for W2 is. So that's the, so if you've got a lattice point in well, you know, like W2 here in that that lower triangle, that's telling you that you do not have epsilon log canonical. If everything's in the bit where W1 is, then you're okay. Oh, I've got through a quarter of the way. Oh, is it all right so far? Can people hear me? Vanya, can you hear me?
Yes, I can hear you. I mute my microphone, but I can hear you perfectly. Yeah.
Yeah, good. Okay, because you see, I'm getting no feedback. I'm just talking to a screen.
No, you're talking to us.
Yeah, no, but yes, but I don't know. I can't tell from whether I get no feel for how the audience is coping. You know, you could all just have logged off quietly and gone to make yourselves more tea, and I wouldn't know.
Oh,
okay. So what happens when we do weighted blow up? So I said you do this weighted blow up. I want to be able to say what that is in toric terms. So it's the toric variety associated with the fan in RD and the standard lattice, which consists of all the faces of all the cones spanned by n and all but one of the EIs. So the EIs are the standard basis vectors of Rn. So E1 is 1, 0, 0, and so on. I just subdivide the basic, the first orthant by putting in this vector n and then just joining it to all the others. Now these cones, the things I've called sigma nj, they're simplicial. I mean, they're spanned by all the e's except one, but n instead. So we always have q factorial singularities. So, you know, one wants q factorial terminal singularities, but q factorial is given to us for free. We don't have to do anything about that. So I just want a bit of notation. So I want the standard simplex to be called delta. And delta 1 is its top face. It's the face at height 1. It's given by the, you know, the equation sum of the variables is equal to 1. So that's just some notation. Okay, and now I want to think about the. I want to go through the thoughts the way that I went through them historically. So I want to think about the terminal case first, because that gives some idea as to why one can do this. So let's think only about that. For the moment, I'm happy to think about any dimension. So we had a criterion for terminal singularities. So that was, so an affine toric variety has terminal singularities if the simplex that defines it in this way, with one of its vertices at the origin, if that's empty. So if ADN, which is not an affine variety because it's had this blow up done to it, if that's, that has terminal singularities if and only if all of those simplices are empty. But if all the simplices are empty, that's the same as saying that their union is empty. And the union is the convex hull of all the E's, all the base vectors, n, which I think as being somewhere far away, and 0. And so what I want to do, I'm going to draw a picture in a moment, is I want to split that convex hull the other way. I'm going to split it into the part above delta 1, and the part below delta 1. So the part above delta 1, I give it the name delta n, so that's the convex hull of all the E's and n. And the part below is simply delta. Okay, but delta is empty. I mean, it's the standard simplex. So if I want to know that, that AND has terminal singularities, it's enough to check the emptiness of delta n. So although AND is a non-affine thing and it has potentially several singularities, and I would have to check each of them, in fact, that being terminal is equivalent to some other singularity somewhere completely different that doesn't belong to it at all, associated with delta n being terminal. So although this is not a question about an affine variety, there's a kind of auxiliary affine variety associated with delta n that I can look at instead. So here's a picture. It's actually the simplest picture you can imagine. I've drawn it in dimension 2, and so the you take your blow up at this point n, and you join 0 to n, and so you see that the two simplices, the top one OE2 n and the bottom one OE1 n, and you want both of those to be empty, but the white triangle at the bottom left, that's empty already, so I only need to test the pink bit. And that's it. I mean, that's basically the only idea I've got in this whole thing. So what I've been telling people is that it's a one-line argument, and there's the line. It's the line E1, E2. You join that. It's a one hyperplane argument, if you like. You join that, and then you say, well, look, everything below it I know about, everything above it, well, that's just a single cone, and maybe we can do something with that. So absolutely simple idea. Okay, so let's go back to the question that Kosha asked. So, so we take D equals 4, and we'll look at terminal singularities. So your first thought is, well, so, I mean, you know, we've got this pink triangle here. Let's move the origin to n. So make a change of coordinates, move the origin to n. And then there's a toric variety. When I do that, delta n gives me a toric variety. And let me see if I know I can see if I can look it up. See if I recognize it on some list of affine toric fourfolds with terminal singularities. So, you know, if I can do that in an exhaustive way, then I've solved the problem. Okay, well, the first thing is that when you do that, you look at the singularity that you get arising from delta n, and it is actually a cyclic quotient singularity. It's always non-Gorenstein. And it's a cyclic quotient singularity. This is kind of convenient. Actually, it turns out that non-Gorenstein terminal fourfold quotient singularities are always cyclic. But that's a special fact in dimension 4. Once you get to dimension 5, you can have quotients by things like Z mod 3 cross Z mod 3 or something like that. But in the fourfold case, if they're terminal, they're all cyclic quotients. But we don't have to worry about that because we've actually got a cyclic a cyclic quotient anyway. So I'm looking at the variety defined by delta n, with the origin moved to n, and I'm saying, let's have a look at that variety. And it turns out that it's an affine variety with a single cyclic quotient singularity, and I want to find out whether that's terminal or not. Okay, well, there's a list of these things. So long way back in 1988, there's this paper of Maury, Morrison, and Morrison. I've never really found out whether they wrote a paper because they thought that they ought to with names like that, or whether they actually whether they actually started talking about mathematics first. But I think the paper is interesting anyway. And what they did is, in mathematics and computation, it's an experimental paper really, and they experimented with cyclic quotient singularities of fourfolds. So this was not long after Maury had classified threefold terminal singularities. But to keep things simple, they looked only at quotients of prime index, so quotients by a cyclic group of prime order. And they made a conjecture. And I'm going to explain what their conjecture is. So, well, the first thing that you need to notice is that terminal quotient singularities in dimension 4 correspond to empty lattice simplices, but you need to, they come in fives, not necessarily all different. Because if you just hand me an empty simplex and say, here, make a terminal quotient singularity out of it, what I'm going to do is pick one of the vertices, move it to the origin, and then put the rest somewhere else using some element of GLZ, but that doesn't matter. But I do have to pick one of the 5 vertices to go to the origin. So there are in principle 5 things I could do, and they might all be different. So you should expect these things to come in 5s. And that's the way that they write it. So they make a list, Maury, Morrison, and Morrison, and the members of the list are quintuples, Q1, Q2, Q3, Q4, Q5. Those are integers. And they are integers, they normalize it so that the sum of the Q's is 0. And then there's also a prime P. For them, it's a prime. And then what you do is you let Z mod P act on A4 with weights any 4 of the QI. So Q2, Q3, Q4, Q5, or Q1, Q2, Q3, Q5. So you drop out one of the Qs and you use the others as your as the weights. So a generator of Z mod, a generator zeta of Z mod P acts by e to the 2 pi I Q1 over P on the first coordinate, and so on. And then the quintuples are such that any of those 5 choices gives you a terminal quotient singularity. So we're going to classify the quintuples instead. So one way to say this is to say, well, look, there's a lattice associated with this, which is the lattice generated by the vertices, but there's also the lattice generated, the lattice Z4. So you take the quotient, that's a finite group, and it's actually a cyclic group of order P, so I can pick a generator of it. And then I can lift that generator back to be a point in my original lattice Z4, and I can express it in terms of barycentric coordinates. I mean, after all, the polytope is the thing given, it's the set of things given by positive sums of the vertices, and I say what those numbers are, and since I'm only interested in things modulo Z4, I can then normally you usually normalize them so that they add to 1, but I can normalize them so that they add to 0 without going, and I'll still be in the same orbit. So that's another way to say it. You don't have to think of it that way. Okay. It actually turns out that the thing that's not particularly important here is P. which seems a bit strange that it doesn't matter what group you act by, but it doesn't, or not very much. So let's say, why not? See, most of the values of Q that occur work for any sufficiently large P. P, for example, bigger than the modulus of any of the QIs. What you actually need is for P to divide at most one of the Qs, I think, if I remember rightly. So most of these Qs work with any P. You can feed those weights. You can take Z mod any sufficiently large P, take the quotient by those weights, and you will get something terminal. And so here's the list. I'm not going to show you the list in full. What they found was 1 minus 1, A, B, and minus A minus B, and then 1 minus 2, A minus 2A, and the thing has to be A plus 1. So those work for almost any A and B. And then there are 29 others. So I've shown you the first of them, 9, 1, minus 2, minus 3, minus 5, and those work, by which I mean they give terminal singularities for any P. Well, I mean, you know, that one isn't going to work for P equals 3, for example, but any sufficiently large P. But there are a few where P does matter, and they call these sporadic cases, and they just computed. And after they got past P equals 419, the computer stopped printing out anything new. It was just printing out these 29 cases and the 2 others that you see for different values of A and B. It wasn't printing anything more. There weren't any more families. There weren't nothing new happening. So at this point, they turned it off. Now, I mean, of course, computers stopped doing things in 1988 rather more readily than they do now. So maybe that wasn't very good evidence, but they'd done actually computed quite a long way. There was fairly good evidence that they didn't have, that there wouldn't be any more, at least of the 29 families. Maybe you might think there might be some more sporadic cases with some larger P, although the evidence against that was also quite good. Okay, well, the conjecture didn't actually last very long, at least not the bit about the 29 families. The first proof of that was given actually by me a couple of years later, and then there's another proof by Bober, which is about 10 years after that. He was doing something entirely different and just stumbled on this as a problem in geometry of numbers. And the other thing we know is that Alexander Borisov showed that the sporadic cases, these ones that only work for a particular value of P, that is actually a finite list. He didn't show that that Morrison and Morrison had found all of them, but he did show that they had found that there were only finitely many more. And from our point of view, that's completely harmless, because I don't mind if there are finitely many singularities I don't know about, because they will not they will not change the existence of a bound. They'll just change what the bound is. So that's actually enough for me to answer the first question, the original question about terminal singularities in dimension 4. Well, it isn't quite, because there's a worry about what happens in the case of composite index. And I don't really want to go into that because it all gets superseded by some later stuff anyway. I did actually know a way around that, but it's no longer of any use because we can do better than that. Okay. Any questions at this point?
So far, so good.
So far, so good. Right. So the thing that actually drives all of these is, well, we didn't know this at the time, but there's a result of a bloke called Jim Lawrence, who seems to be interested in combinatorics geometry of numbers. And Borisov found this rather hidden paper of his, which, and this is what he used, what Borisov used to prove that there are only finitely many cases not known about by Morrison and Morrison, prime case. So this really is the key to everything else. And what it says is this. So I'll fix an open, I mean, we can open slightly, but it doesn't matter. An open subset of R to the D. And I'll take a closed subgroup of R to the D that contains the integers. And the statement is that among all the subgroups of G that contain the integers and miss U, those are contained in finitely many maximal subgroups of that kind. So you need to read this result carefully. By maximal, I mean maximal subject to all the conditions that follow. So they're not just maximal subgroups of G, they're maximal among subgroups of G that contain the integers and miss U. Okay, so any subgroup of open face G that contains the integers and misses U is contained in at least one of finitely many such subgroups of G. So Lawrence's paper says it's about subgroups of the torus because he works with RD mod ZD, and of course we could say it all that way if we wanted to, but this is quite convenient for us. Okay, so let's think about empty or hollow simplices in dimension 4. So really quite recently, Paco Santos and Iglesias Valinho, I think is his research student, used Lawrence's theorem and some really quite subtle estimates, some knowledge of lattice polytopes in lower dimensions, and their proof is basically by induction on the dimension, and a lot of computation to give a complete classification of all hollow lattice simplices. I think I mean hollow, not empty, in dimension 4. Do I mean, maybe I should say empty there. I'm sorry, yes, that should say empty. I've written hollow both in the title and on the 4th line of that slide. Those should both say empty because it's terminal singularities, not canonical singularities that we know about. So that's essentially the equivalent to classifying terminal 4-fold quotient singularities of arbitrary index. And they've done it completely. So it subsumes the Morrison paper, it subsumes my earlier paper. Everything is now known. What they found was, I mean, this is not essential for what follows. What they found is that the Morrison list is basically correct in the sense that there's still nothing new beyond index 419. They found some discrepancies between their computations and the computations as stated in Morrison, which are either caused by misprints or by double counting. It's not always immediately obvious if you've got 2 quintuples whether they're the same or not. It's not just a matter of permuting them. This is for the sporadic ones where you've got a fixed P.
Gregory, there's a question from Mirka.
Yes?
Mirka, can you ask? Are there abelian quotients?
These are all quotients by cyclic groups. I mean, we already know that, so we're looking at terminal non-Gorenstein singularities. And we're interested in the quotient singularities. So a terminal singularity has it has a canonical cover. I mean, canonical in the sense that the cover has canonical singularities. It's always, this is an observation made by Nick Shepherd Barron a very long time ago. And so one way to get a terminal singularity is to take a smooth point and have some finite group action, and then it has to satisfy some conditions. And we know from work of Morrison and Stevens and various other people that the quotients that you're interested in are here there would be abelian ones, but in dimension 4 the only terminal ones come from cyclic quotients anyway, so this is something we already know. It wouldn't matter for us if we didn't know that, because the quotients we are interested in are cyclic ones anyway. So yes, these are really, it really is what I've said there.
Thank you. Thank you. Mm-hmm.
So what they find is, as I say, there are some discrepancies which, because we no longer have the calculations of Morrison and Morrison, we can't really find out what went wrong, but they seem to be very minor. And then in the case of composite index, you get some more families, which are kind of like, they're sort of limits of the other ones. They're not too bad. And there are 17 more families to add to the 29 you have in the prime case. And then there are some more sporadic ones, which in any case I don't really care about. But because I now know what all the terminal fourfold singularities are, I can hope not only to prove, not only to give an answer to Birkar's original question, but actually to find a precise bound. And that's what we do. We compute this precise bound. So the worst case from our point of view, the one with the biggest n min, is this one, 32, 41, 71, 102, with index 245. So it's the quotient of z mod by z mod 245 with those weights 32, 41, 71, 102. That's the unique one where the minimal weight is as high as 32. But I can get the minimal weight to be 6 by taking any index. The index is called V because from another point of view, it's the volume of something. So the index, any index that's at least 37 and co-prime to 30, you have this one, you have V minus 30 and then 6, 10 and 15. And the action of Z mod V with those weights, that's always, that gives me terminal singularities always. And obviously you can have, there are infinitely many of these, all with minimal weight 6. So we definitely can't do better than those. Okay, so that's the situation for terminal singularities. Terminal fourfold singularities. So now let's go back to arbitrary dimension and to epsilon log canonical, which is, so we've now answered the question we were asked in the pub, and we're trying to answer the serious question. But the first step is exactly the same. You get a similar, you get a statement about when a dn has epsilon log terminal or epsilon log canonical singularities, and it's if and only if epsilon delta n, so delta n just shrunk by a factor epsilon towards n, towards 0, is empty or hollow. So essentially it's the same picture as we had before, just the one with the pink triangle in, but just everything is scaled by a factor of epsilon. You need to think for a moment whether to verify that that's the case, but it is. And I don't need to have the condition about the about lattice points on the top surface anymore either, because that's automatic. Okay, well, the correct change of coordinates, and I think this was the first thing that Paco did when he saw what I'd written, is you make an affine linear change of coordinates by moving n to the origin. You leave the EIs alone. So that determines an affine linear change of coordinates. and then the origin moves to a point I'm going to call P, which is n scaled by this number -1 plus the sum of the weights. So I want to give that a name, that -1 plus the sum of the weights. That's V. So P here is a point in real d-dimensional space. And I also want to introduce the group lambda P. So this is the group that I get by taking the integers and then chucking in this rational point P as an extra generator. Okay, and then I'll get to rewrite this criterion in those terms. So I just make this change of coordinates and it turns into this thing. So again, there's a little bit of checking to be done. It's rather easy. And it turns out that the criterion for ADN to have epsilon log terminal canonical singularities is that this thing delta P epsilon is empty or hollow with respect now to the, I've said the lattice, I'll leave that for the moment. So this is an overlattice of ZD. It's the overlattice generated by the integers and P. So delta P, I was going to say this here. I'll say it now anyway. This delta P epsilon, what that is it's delta, just the shrunk by a factor of epsilon towards P. I mean, you go and stand at P, and then you do a homothetic towards P by a factor of epsilon. You see what it does to delta. That's what that is. Okay, so what we did here was to start with n, and then we introduced this point P. We actually want to look at it the other way around. We want to start with P. So I want a set called, the set omega is, so in the LaTeX file that produced the paper that we've written, my notation for this omega is \outside. It's it's everything in the, it's an open set, it's everything in the first quadrant, relatively open set, everything in the first quadrant that's not in delta. And for those things, well, because it's not in delta, I've got a P which is in omega, and so the sum of the PI's isn't 1, or you would be on the top face of delta. So I can write down V, which is 1 over -1 plus the sum of the P's, and I'll call that the index of P. And I'll write down VP, we call that N, and these are called the weights of P, and the smallest weight of P is the thing called N min. Now, so this is a statement about what delta PE is, how P epsilon is, and what lambda P is. Now, again, I want lambda P to be ZD, the integers plus ZP, but this doesn't have to be a lattice anymore because P now is a real point. It doesn't have, I don't require it to be rational anymore. So if it isn't, then this will be some funny subgroup with some closure being maybe of positive dimension, and that's going to be important. So it doesn't have to be a lattice, but I can still use all the terminology that I had before. And then I'm going to say that the point P is epsilon hollow. So this is just a word we're using. If that shrunk copy of delta is hollow with respect to the group lambda P, that's to say lambda P misses its interior. So that's going to be the sort of thing we're going to use Lorenz's theorem for. You check, incidentally, that the V that we have here is the same as the V we had before. I defined V in terms of the P's now. And then I've ended up with something I called N, and given that N, you could say, well, I'll look at -1 plus the sum of the N's. Isn't that V? Well, yeah, it is. Okay, so the basic bound that we get here is, you get it the following way. You take So I'm going to have H1 is going to be the affine hyperplane containing delta 1. So just take the thing that goes through all the basic generators, and H0 is the linear hyperplane behind it. So HT is x1, is the sum of the coordinates is t. And I'm going to choose a linear subspace in RD of codimension k. I'm going to assume that it's not in H0. So this linear subspace is not parallel to the top face of delta. And under those circumstances, we're going to find a bound depending only on L for the minimum weight of the points in omega, such that L translated so as to go through P misses, what it misses is the interior of the top face of delta. So just stick with that for a moment. So let me try and explain where this bound comes from. So I'll look at the projection. So I'll just kill off L. And this is a map from RD to something isomorphic to R to K. And it's skew in the sense that if you look at the images of the generators of delta, you call those SI, they're linearly independent, affine linearly independent. They don't line any affine hyperplane, because otherwise L would be contained in H0, just be projecting partly parallel to the top face of delta. And that's useful because I can make the following definition, which is for any old hyperplane now in the R to the K, so after I've killed off L, LH is the minimum over all these S's of the distance from H to 0, the height of H above 0, divided by the distance of H to S. So this is big if H is very close to the SIs, and I'm looking at the minimum of the SIs that don't actually land in H. So this thing on the bottom is non-zero. And so that makes sense. There are SIs that don't land in that H. Okay, so now the next thing is that P plus L, so this is this translated L, it can't meet delta naught. And the reason it can't meet delta naught is, well, P is, and we've got a picture here, P is in omega, so P is outside. If it met delta naught, then it's very straightforward. That red dotted line is in L. Well, it's parallel to something in L. It's been translated so as to go through P. So that's a bit of P plus L. And to get from P to the point in the interior of delta, it has to go through a point in the interior of delta 1, the interior of the top face, which is that diagonal blue line. So that tells me that the L projection of P is not in the interior of the L projection of delta. So I can pick a hyperplane, and I'm going to pick a facet supporting hyperplane. I'm going to can do this from among the hyperplanes that contain some facet of the polytope that I get by projecting delta, which weakly separates pi L of P from pi L of delta. By weakly separates, I mean it is a facet supporting hyperplane, so it's not so pi L of delta isn't at a positive distance from it, but pi L of P is. And then I lift that back to a hyperplane in R to the D, and it separates L plus P from delta. I've lost facet supporting. It doesn't have to be a facet supporting hyperplane of delta, but that makes no difference to me. Well, I'm going to assume that this H tilde doesn't go through the origin, because if it does, one of the weights is 0. So if it doesn't go through the origin, then I can say, well, I can define it by saying it's at height 1 relative to some A, and because H delta separates H tilde, I'm sorry, separates delta from P, so A dot P is telling you that A dot P is greater than or equal to 1 because P is above H tilde, but it separates delta from P, so anything in delta is on or below H tilde. Among the things in delta are the EJs, so the EJs actually be A dot EJ. That's less than or equal to 1 because the whole of delta is below H tilde, and A dot EJ, that's just AJ. So the AJ is just the jth coordinate of A. And now we do a little calculation. And so you look at the sum 1 minus A NJ, and you break this up in an appropriate way. And what you find is that this is less than or equal to 1. But these terms on the left here, so they are positive because 2 lines above we have that AJ was actually, they're non-negative because AJ is less than or equal to 1, but they can't be bigger than 1 because all these terms are non-negative and they add to 1, so they can't. None of them can actually be any bigger than 1. Okay, so now we just do the rest of the calculation. The distance from H tilde to 0 is 1 because we set it up that way, and the distance from H to EI is 1 minus A dot EI, and so the thing that we want the thing that we're looking at, the expression that we're looking at is 1 minus AI. So the skewness tells us we can pick an S, an image of one of the E's, one of the corners, which is not in H, and now we get that we had that 1 minus AI, NI was less than or equal to 1, so NI is less than or equal to 1 over 1 minus AI, which is this ratio of the distances. LH is the biggest of those distances over the H among the hyperplane supporting facets, and I'm sorry, over the SJs, and then L was you maximize those among the H's. So that gives us the inequality we wanted. So one of the NIs, but we weren't able to control which one, is bounded by this number here. So that's really the kind of core computation, and this is actually enough now to deal with arbitrary dimension and canonical singularities. I'm not going to bring epsilon into it just yet. So how does that go? Well, we're going to use Lorenz's theorem. So there's a finite collection of closed subgroups of R to the D. So for the moment, my open face G is the sort of universal closed group is the whole of RD. So these are the finite collection of closed subgroups of RD that contain Z to the D, miss delta 0, miss delta naught, the interior of delta, such that if you've got any subgroup that does that, it's contained in one of these G1 up to GT. Okay, so I'm going to use L for the identity component of G. So LJ is the identity component of GJ. These GJs are automatically, they're closed subgroups, so they're Lie groups. They're just some copies of some linear space, and that linear space is LJ. And then what you do is you project now not by killing off L, but by killing off H naught. So you project parallel to that top face of delta. And so this gives me a subgroup. GJ now becomes a subgroup of R, and because the identity component was in the kernel of this projection, what I have here is a discrete subgroup of R. So in other words, I've just I've got rid of the identity component. The group GJ consists of some linear subspace translated by some stuff, and it's the translations that I'm interested in. So those are elements of R. And it's a discrete subgroup, so I start at 1 and I go up and I ask, how soon do I come across an element of R? What's the next element of R I come across after 1? This is an additive subgroup of R, but I can still ask, what's its first element bigger than 1, because it's a discrete subgroup. And then you call that Y, and then the right thing turns out to be to look at, you have to turn it around, you look at LGJ is 1 over Y minus 1. And when you unwind everything, what you get is that the index V, and therefore each weight as well, of every P in GJ intersect omega is bounded by that number, LGJ. Well, here we work with just one of the G's, but, well, LJ isn't contained in H0. And so the L plus P, we had this earlier, L plus P, it misses delta naught. And so there's an LGJ, which has, depending only on LJ, for which this N minimum is less than LGJ for every P in GJ intersect omega. And then the bound that I want is just the maximum of those over the finitely many G's. So what I'm saying is you choose your P, you find out, you look at the lambda P that you get, that lives in one of these finitely many closed subgroups, and you look at the bound associated with that. And then because there are only finitely many of them, you get everything. So that's really the thing that gives us a bound. So I said everything I was going to say. I think I didn't want to say that. I think that's the typo. I think you ignore that. So what I want to do in the last minute or two is just to give a very quick indication of the sort of thing that one has to do to make this work for arbitrary epsilon. So what you do is you wander around delta 1, the top face of that simplex, and you make a local computation. So there's a bound and an open neighborhood of X in RD, not in delta, but actually in, wandering it off delta as well. And you look at P, which is in omega, so it's above delta 1, but it's in this neighborhood WX, so it's close to X. And if that's epsilon hollow, so the lambda P misses the thing that it misses, then the smallest weight satisfies this inequality, the smallest. So very near to X, epsilon hollow things have bounded weight. And then, well, the proof of this was the thing that it took us a long time to get right. It's complicated. It's elementary. I mean, there's nothing. You don't have to use any sophisticated machinery, but it's you have to do sort of unexpected things. So you look at you look at shrinking delta towards Q for all Q, and you take the interior of the intersection. So all the points that are inside. All the epsilon shrinkings of delta towards points sufficiently near X, and then you apply Lorenz's theorem. But it's complicated. You need to do this for each U in a countable basis of neighborhoods, and then there's a complicated induction, a double induction. And I think Paco and I each had a version of this, a way of organizing it. And I think mine was the first one that actually worked, but his was marginally less confusing, so that's what we've written in the paper. But there are various ways of organizing it. It's a messy double induction. And then after that, you just use a compactness argument. I mean, you've got a neighborhood of X that does something all over delta 1, and delta 1 is compact. And then after that, you have an argument similar to the one for the canonical case, and that finishes it. I think I've said everything I was going to say.
Okay, thank you very much, Gregory. I applaud, and I think everyone should applaud as well. So, is there any questions? Any questions to Gregory? For example, we have Sasha Borisov here, Kostya Shramov. So, any questions? Okay.
I have a question.
Yes, Mirka, please.
When at the beginning you said that there could be Mori contraction which are not weighted blow up. What do you mean Mori contraction towards what?
As I say, this is something I learned from Tom Duckett. So again, I may be misrepresenting him, but the statement of Kawakita's theorem says that you have a Mori contraction to a point. But I think so, meaning that the indeterminacy locus of the well, it turns out to be a blow up is just a point. But I think what can happen is that you can have Mori contractions that are not weighted blow-ups, but the unpleasantness is hidden in the unpleasantness of the. So you have some curve, maybe something like a singular curve in a, I don't know, fourfold or fivefold, something like that, and you can build something which obeys the rules. I mean, it's the fibers is a Mori fiber space. The fibers, so everything has Q factorial terminal singularities, but it's not a blow up because it's not a weighted blow up. It's a blow up maybe of some more complicated ideal sheath supported on,
May I add?
Yes.
Gregory, so I think, for example, if you have like fourfold, if you blow up a point,
yeah,
and then you take a quadric and exceptional divisor, and I think if you blow up it, and if you then contract back, something like this, if you contract back,
yeah, it's something like that. I think you can probably do it with a curve in a fourfold. I mean, your example is even over a point, or no?
Something like this. So I think this is not going to be terminal, but in high dimension, I think you can do this. So it's not going to
yes, I believe so. As I say, this is something Tom Duckett showed, and he said it was mentioned in possibly in the book of Kolanabuchi and that one. I mean, he told me where to find it, and I've forgotten, I'm afraid. He's not here, is he? I don't see why he would be. He came to this talk last time. Why would he want to listen to it again?
Basically, this means there's no generalization of Kawakita theorem like direct like this in high.
No, I mean, essentially because you can make the Kawakita has his indeterminacy locus as a point, and if you have high dimension, then you can make the indeterminacy locus be unpleasant, and then you can make strange things happen.
But you mean that the target of the Mori contraction is still smooth?
Yes.
Yeah. Okay.
Any more questions? Sasha, any question? Kostya, any question? Chen, any question? No? Okay. Okay, if we have no more questions, let's thank Gregory again. And thank you very much. And I upload this talk and send link later. Gregory, thank you very much. Yeah.
Thank you.
Yeah. Thanks. Bye. I'll okay. There's something. There's clap in the chat. So
yes.
Okay.
Thank you.
See you. Bye. Thank you very much.
Bye.
You stay safe. Yeah. Bye.